When a covalent bond forms, it can be either polar or nonpolar. In a nonpolar bond, the difference in electronegativity between the two atoms forming the bond is less than 0.4. And this means that there is an equal sharing or an equal distribution of electrons between the two nuclei. If you have a polar bond, it means that the difference in electronegativity is 0.4 or greater, but less than 1.67. And this means that the electrons are attracted to the nucleus of one of the atoms in the molecule more than the other, one atom in the bond more than the other, causing one atom to be partially negative and the other would be partially positive. So for example, the bond between hydrogen and carbon would be a polar bond. It has a difference of electronegativity greater 0.4 or greater, but still less than 1.67. So when you form methane, methane behaves like a non-polar compound, even though each one of the 4 bonds in methane is polar. So how can this be? Well, when you're determining if a molecule is polar, you can't just look at the individual bonds. The individual bonds play a part, but it is vector addition. The dipole moment between hydrogen and carbon, these arrows, are a dipole moment. They show the positive pole, where the plus sign is on the arrow, and the negative pole, where the arrow is going. So there's a greater electron density around carbon. But how does this cause this? So how can 4 polar bonds cause methane to be nonpolar? Well, you need to refer back to your VSEPR models and your molecular geometries. When you're adding dipole moments, they add together geometrically, meaning for every one that goes left, you should have, to cancel it out, you need one that goes right with an equal magnitude. If the magnitudes are not equal, they won't cancel each other out, and we'll have what's called a net dipole moment. Since all 4 bonds to this carbon are identical, they cancel one another out. And since they're all at equal angles to one another, they'll cancel each other out. So there will be no net dipole moment for the methane molecule, because these vectors are not going to add up to anything other than 0. And therefore methane is nonpolar. Let's look at water. Water has a great difference in electronegativity as well between hydrogen and oxygen. Therefore we have a polar bond where hydrogen is less electronegative than oxygen. Therefore the electrons are going to be moving towards the oxygen in the case of both hydrogen to oxygen bonds. If we were to add these two together, meaning if we took these vectors out and, let's see if I can do it here, and we overlap them, we would see that they would sum together to equal a net dipole moment through the center of this oxygen, with the partial positive end being down here with the hydrogens and the partial negative end being on the oxygen. Also, oxygen has 2 lone pairs, which are automatically automatically negative. And if you have lone pairs and they aren't going to cancel one another through their VSEPR model, and we'll see an example of that in a little while, you will most likely have a polar molecule. Polar molecules respond to a magnetic field where the partial negative end lines up with the positive pole, and the partial positive end lines up with the negative pole. Let's look at methane again. When all 4 bonds are the same, there is no net dipole moment. However, if we change one of those 4 bonds, it's going to change that net dipole moment. So while methane may be nonpolar, methyl chloride with 1 chlorine will be polar, because now the dipole moment of these 3 hydrogens are not going to cancel out the dipole moment from the chlorine to from the carbon to the chlorine, and therefore the net dipole moment will move through the center of this atom towards the chlorine. We replace another one of those hydrogens with a chlorine, dichloromethane. Now we have a much greater pull through the center between these 2 chlorines, because it's going to add together the dipole moment from this chlorine, dipole moment here, and move straight through the center. Trichloromethane, replace another hydrogen. Our dipole moment shifts slightly and is away from the hydrogen through the center of the atom. But if we replace all 4 hydrogens with chlorines, now we have a dipole moment for all 4 that will cancel each other out, and there will be no net dipole moment. So the moral of this whole thing is, if the octet rule is obeyed and all of the surrounding bonds are the same, then the molecule is nonpolar, since the dipole moments cancel each other out. However, if you have, air quotes here, oddballs, such as lone pairs or different elements, this will cause a dipole moment of some sort. So, summary of all chemical bonds. Chemical bonds are forces of attraction that hold groups of atoms together within a molecule, or if they're an ionic compound, within a crystal lattice. It makes them function as a molecule or as a unit. Ionic bonds are when electrons are transferred from 2 atoms with extremely different electronegativities, greater than 1.67. Compounds that form ionic bonds typically form solids, and they are a combination of metals and nonmetals, because metals can form cations and nonmetals can form anions. The strong attraction between a positive and negatively charged ion is what keeps ionic bonds together, and because this attraction is so strong, they have very high melting points and boiling points, and they also take a great amount of energy to separate. They are excellent conductors of electricity in both their molten state as well as dissolved, and the formulas for ionic bonds are the simplest ratio of one element to another. So for sodium chloride, which forms a crystal lattice, all of these will form a crystal lattice. They'll form several sodiums surrounding several chlorines surrounding several sodiums. The simplest ratio is 1 to 1. So that's what we write as its formula. Same with magnesium iodide, 1 to 2. Calcium phosphate, 3 to 2. Covalent bonds are when electrons are shared between 2 atoms with similar electronegativities. So the difference between them would be less than 1.67, but greater, or less than 1.67. If the difference is less than 0.4, we have a nonpolar covalent bond, meaning that they share electrons similarly, and there is no dipole moment. However, if the difference is 0.4 or greater, we have a polar covalent bond, and one end is partially positive and one end is partially negative. The formulas for covalent bonds are the actual ratios of one element to another. So for methane, 1 to 4, arsenic diarsenic pentoxide, 2 to 5, glucose, 6 to 12 to 6. We don't simplify that down because covalent bonds show the actual ratio of one element to another. Covalent bonds, because of their intramolecular forces being less, and that's the topic of our next unit, because their intermolecular forces are less attractive or not as strong as ionic bonds, have lower melting points and boiling points. Also, covalent bonds form between nonmetals. These are nonmetals that form with nonmetals, and nonmetals are poor conductors of electricity. Therefore, covalent bonds are poor conductors of electricity. There is a third type of bond which you are very rarely tested on, but it is metallic bonds. These are substances that are metals. And the way that a metal forms, it is a It is a positively charged center surrounded by a quote-unquote sea of delocalized electrons. These electrons are free to move between these cations, and these cations, being attracted to those electrons, hold it together. They form solids at room temperature, and they have a wide range of melting points, with the exception of mercury. Mercury is a liquid at room temperature. It is the attraction between the metals and the electrons that keep it as a whole, and they are excellent conductors of energy because of these free-floating electrons, which can move from one place to the next, giving them the ability to do electrical work. When we write the formulas for metallic bonds, we simply write it as a neutral element or a neutral atom. Most chemical bonds are somewhere between purely ionic and purely covalent. And that is the end of chemical bonding for now.